Okay, so yeah, thank you, Kasra, and I'm really excited to be here, and I want to thank the organizers again for hosting this amazing workshop and also for the invitation to speak. So today I want to tell you some of our recent work on developing rotation averaging methods based on fast Laplacian solvers. So this talk is based on a recent paper in collaboration with my advisor, Professor Jonathan Hao. And in the paper, we also have a deeper dive into both the theory and also experimental results. So if you're interested, I will encourage you to check out the paper for more details. So as I mentioned, this talk will be focusing on rotation averaging or rotation synchronization problem. And we have already seen kind of a very good review of this problem in the previous talk. But as a quick reminder, in rotation averaging, the goal is that we want to estimate n rotation variables using noisy relative measurements. So this problem can be visualized as a measurement graph where each vertex in this graph corresponds to one rotation that we would like to estimate. And then each edge corresponds to a noisy relative measurements. So the underlying or the corresponding optimization takes the form of a nonlinear least squares, where we want to estimate our n rotation matrices by minimizing the weighted sum of squared measurement residuals. So for each relative measurement R tilde ij, there is also a corresponding constant kappa ij, which reflects the precision of that measurement. And here on this optimization formulation, D is a distance metric on the rotation group. And in this talk, I will consider two of the kind of the most popular choices for D. One is the geodesic, or also known as the angular distance on rotation. And the other one is the chordal distance. So the theory and also the algorithms that I will present to you today will work equally for either of these choices of distance metrics. So rotation averaging, as you have seen right now, it's a very fundamental problem, and it has many applications in both robotics and in computer vision. So in robotics, there's this problem of simultaneous localization and mapping. And in computer vision, there is a closely related problem of structure from motion. So in both of these applications, rotation averaging will appear as a critical subproblem that is very essential to the overall application. And in the past, researchers have also already investigated the role of the graph structure for rotation averaging from many different angles, and that have leads to many interesting results. So I'll present to you some of them on this slide. So there is one line of work that study the role of the graph structure through this estimation theoretic perspective. And more specifically, we can show that actually the Fisher information matrix underlying the rotation averaging problem is given by a graph Laplacian. And more recently, there are also kind of more diverse angles of looking at graph structure and rotation averaging. So there is the perspective of spectral relaxation that we have already seen. There is also studying the role of graph structure on the local convexity of the rotation averaging problem, as well as strong duality. So when we view these three kind of recent directions, although they look very different, and they are indeed very different in the underlying technical approach, they all share a kind of a common theme in the sense that the final performance bound that we derive from these directions, they all depend on the graph structure through the algebraic connectivity, which is the second smallest eigenvalue of the Laplacian. And in the meantime, there's also the yet another line of research that tries to tackle rotation averaging from the perspective of optimization. So how can we develop efficient optimization methods to solve the rotation averaging problem? And this talk will be more related to this last line of research, where it's more focusing on the optimization perspective. So the key points that I want to convey is that when we consider rotation averaging as a Riemannian optimization problem, the core part of the computation actually reduced to solving a special type of linear system, which is called the Laplacian linear system. So this is really just a standard linear system, but the matrix is given by L, which corresponds to a graph Laplacian. So I will show how we can leverage this interesting observation to develop new optimization algorithm for rotation averaging, And I will also talk a little bit about the application of this idea in the multi-robot setting. So to get started, a little bit more background on Riemannian optimization, which is relevant for this talk, because when we treat rotation averaging as an optimization problem, it is an optimization problem defined on the matrix manifold, namely the rotation group. So on this slide here, I'm showing a generic framework for performing Riemannian optimization. So as you can see, it looks very similar actually to a classical iterative optimization scheme on the Euclidean space. But the main difference is that at every iteration, we need to compute our update vector, which is restricted to the tangent space at the current iterate xk. So pictorially, you can view this tangent space as providing all of the directions that we are allowed to move while still respecting the geometry of the underlying manifold. And once we're able to compute this update vector vk, we could use vk through this retraction, which will map the tangent vector back to the manifold and give us the next iterate, which is xk plus 1. And we can continue to do this in the iterative fashion until convergence. So this is what kind of a generic Riemannian optimization looks like. And in the case of rotation averaging, what I propose we start looking at is by looking at the Newton's method. So this is the Newton's method extended to the case of Riemannian optimization. But still, the core form of this algorithm looks very similar to the counterpart in the classical Euclidean case. So basically, at every iteration, we will compute our update vector vk by solving a linear system that involves the Hessian and the gradient. But in this case, both the Hessian and the gradients are now extended. So they are now the generalized version of Hessian and gradients to the case of Riemannian optimization. But at the end of the day, the update vector is still computed as the inverse of the Riemannian Hessian times the negative of the Riemannian gradient. So the reason that I motivate Newton's method is that it is known to be one of the fastest optimization algorithms in general. So you can actually prove that locally Newton's method always achieve a superlinear rate of convergence, which is very fast. But at the same time, the fast convergence rate also comes at the expense of a slow computation at every iteration. So this is because at every iteration, we need to solve a large linear system involving the Riemannian Hessian matrix. And to make things worse, this Riemannian Hessian matrix, it also depends on the iterate, which means that at every iteration, we need to recompute and refactorize this Hessian matrix. So this is where the kind of the key result that I want to show you in this talk becomes relevant. So the key result essentially states that instead of worrying about this exact Newton step, which it requires solving or inverting this Riemannian Hessian, we could actually approximate this linear system by an alternative linear system where the left-hand side is replaced by the Kronecker product between the graph Laplacian and the identity matrix. And furthermore, by using the properties of the Kronecker product, we can further simplify this linear system in the middle into the matrix form in the bottom, where now the capital VK and the capital GK represents the matrix version of the update vector VK and the Riemannian gradient. So this looks like a pretty magical result. And the underlying kind of theorem, theoretical justification is that we can show that if we look at the rotation averaging problem, and it happens to be that if all of the measurement residuals in our rotation averaging problem are small, then there will be a constant delta, which is a small positive constant, such that the true Hessian matrix is bounded between two scalar multiples of the Laplacian. So for smaller values of this delta constant, this inequality will imply that the Laplacian matrix is a very good approximation of the exact Riemannian Hessian. So to provide you some additional insight, I also have some numerical validation of this theoretical result using synthetic rotation averaging problem. So on the right-hand side, what I'm visualizing is the empirical evolution of this approximation constant delta as a function of measurement noise in the rotation averaging problem. So for each level of measurement noise, I will compute numerically the value of delta such that this inequality holds. So another way of saying this is that this plot here is trying to visualize the tightness of the Hessian bound obtained from the Laplacian. So basically the main observation is that as the measurement noise decreases, the Laplacian will becomes a better and better approximation of the exact Hessian. And we can also compare the quality of this Laplacian-based approximation with a more naive approximation where we try to bound the exact Hessian using the identity map. So kind of intuitively, you can imagine that the corresponding approximation constant, which I'm calling delta prime here, will now depend only on the extreme eigenvalues of the Hessian matrix. But the observation is that, once again, the Laplacian provides a much better and much tighter approximation of the exact Hessian, even in a regime where the noise level is very high. So a quick recap of what I've talked about so far. So the main thing that I'm trying to advocate for is that instead of worrying or implementing Newton's method, we could instead go for an approximate Newton method, where at every iteration, we compute our update vector by solving a Laplacian linear system. And it can also be shown that this approximate version of Newton's method is not a random method. It is actually a Gauss-Newton method in disguise. And some of the immediate computational advantages of this new method is that, first of all, if we compare the graph Laplacian and the Hessian matrix, the graph Laplacian is actually a smaller dimension matrix, which means that computing its factorization or inverse is in general more efficient. And the second advantage, which is perhaps the more kind of significant advantage, is that unlike the Hessian matrix, the graph Laplacian L is a constant matrix, so it doesn't really depend on the iterate. So what that means in a practical implementation of this method is that we only need to compute the factorization of L for once, and then throughout our iterations, we can reuse this factorization. So this could imply very significant computational savings, especially for problems with very large dimensions. Okay, so in the remaining part of my talk, I want to tell you a little bit about how we can leverage this idea behind Laplacian solvers in multi-agent setup. So this is partially motivated by applications in robotics, where sometimes we have to perform collaborative localization and mapping for a team of robots. And naturally, the corresponding optimization problem will now involve variables from multiple agents. So kind of in the multi-agent setup, then the key idea is that we can develop a distributed procedure to solve this Laplacian system at every iteration. And next, I will present to you one way that we have developed to be able to approximately solve this linear system under the server-client architecture. So this is a communication architecture in which there is a special node called a server who is responsible for coordinating the communication across the agents. But otherwise, the underlying computation that is needed to solve the linear system is still distributed across both the server and also all of the participating clients. So we can start by visualizing what the measurement graph looks like in the multi-agent setting. So essentially, we'll have the original global measurement graph, but now this measurement graph will be partitioned into multiple blocks, where each block corresponds to the optimization variables from one robot. And the key idea behind the design of this distributed optimization is that we can leverage a decomposition of this global graph. So what I mean by graph decomposition is that we can first identify a smaller subset of vertices, which I'm calling the separators. So these on this toy graph, these are shown as these 4 vertices that are circled in black. So the separators are important because given these vertices, we can see that the remaining vertices will form this interior. And furthermore, each robot's interior will be completely disconnected from others. So for example, if we look at the blue robot, the blue interior is completely disconnected from the green or the red one. So this partitioning at the graph level is useful because it also implies a corresponding partitioning on the linear system. So if we look at the update vector V that we want to compute, we can also partition V in such a way that there is one component that corresponds to each interior, So for example, V1 corresponds to the green interior. And there is also a final component, which I'm calling VS, that corresponds to the set of separators. And so if we use this partitioning that I described, and we use this to expand the Laplacian system that we want to solve at every iteration, it turns out that the resulting linear system, when expanded, it has a very special sparsity structure, where this Laplacian on the left-hand side actually looks like an arrowhead, where all of the off-diagonal blocks within the interiors are zero. So one way to leverage this special arrowhead structure to solve the overall linear system is using the so-called Schur complement trick. And this trick is widely used in many different scenarios. And essentially it works in two stages, where in the first stage, we first only solve for the separator, which is the VS. And in the multi-agent setting, we'll let the server to perform this computation on the separator component. And it turns out to be possible and also kind of efficient as a result of this special arrowhead structure. Basically, because of this special structure, the server can solve for VS if it is able to aggregate these Schur complements from each robot. So once it's able to aggregate this information, it can use this equation to solve for VS. And in the second stage, given the separator solution VS, the robots can perform a standard back substitution, which allow them to recover the corresponding interior solutions. So if we think about how we use this Schur complement trick in the Riemannian optimization setting, so essentially what happened is that at every iteration K, we'll use this Schur complement trick, which I described in the previous slide, which allow the robots and the server to collaboratively solve this Laplacian system. And again, the server will be responsible for recovering the separator, and the robots will be responsible for recovering their corresponding interior in parallel. So there's one challenge still that which makes this a little bit challenging to implement in practice, and that is related to the cost of communication. Namely, these robots need to upload these matrix SI to the server. And because SI is a Schur complement, it is usually dense, which means that it's expensive to communicate. So this is where kind of once again, the graph structure of the overall problem comes to the rescue. So the core observation is that although SI is a dense matrix, we can show that it is itself still a Laplacian. So that allows us to utilize a family of algorithms called spectral sparsification to compute sparse approximation of these SI matrix with provable guarantees. So once we have these S tilde I, which are the sparse approximation, the way we can leverage them is kind of straightforward. So instead of having the robots upload SI, they just upload S tilde I, and then the server will use S tilde I in its computation. So this will help us gain lots of communication efficiency. And what it ends up doing is that now at every iteration, the robots and the server are now collaboratively obtaining an approximate solution to the original Laplacian system that we want to solve. So using this machinery of Laplacian solvers and spectral sparsification, we can also perform an analysis on the overall convergence of the method. So on the slide, I will just show you a high-level overview of what this analysis looks like. So if you recall, we start from the exact nuisance method, which require us to solve a linear system that involves the exact Riemannian Hessian. And in the first part of this talk, I showed to you that we can actually replace the Hessian with the graph Laplacian. And then there is a corresponding approximation constant, which I'm calling delta here. And it turns out that in the multi-robot setup, applying sparsification actually transform this original Laplacian linear system into a new linear system. And then there is also an epsilon approximation between this new linear system and the original exact Laplacian system. So at a high level there, you can see that there are actually two approximations going on in this algorithm. So there's first a delta approximation going from the Hessian to the Laplacian. And then on top of that, there is an epsilon approximation, which corresponds to the use of sparsification in the multi-robot setting. So intuitively, we'll expect that the final convergence of the method will depend on both delta and epsilon. And that is indeed the case. And so I won't go into the full detail of this convergence proof, but essentially the main result that we prove in the paper is that our algorithm will achieve a local linear convergence. And furthermore, the convergence factor gamma will depend on the sum of delta and epsilon. So before I conclude, let me show you some quick experimental results. So this is evaluating the proposed method, multi-robot method on a large-scale rotation averaging problem. So these color curves corresponds to the convergence of this developed new solver, where different color corresponds to different setting of the sparsification parameter. So you can see that with different setting of this parameter, they still converge at a much faster rate compared to baseline methods such as Riemannian gradient descent or the accelerated version of Riemannian gradient. So this is expected because these baseline methods, they belong to first order optimization techniques, whereas the methods that I present to you today, it belongs to approximate second order optimization. And the true benefit, or the core benefit of using this Laplacian solver is that it also allows us to achieve communication efficiency. So as the right-hand side plot shows, by increasing this sparsification parameter epsilon, we get increasingly more communication efficient variant of the algorithm, but at the expense of a slight degrade in the convergence rate. So in conclusion, in the talk, I presented to you some recent work for rotation averaging based on the idea of solving Laplacian linear systems. So the core benefit compared to the exact Newton is that it is much more computationally efficient. And I also presented to you some application in the distributed setup. So I think overall, this is kind of a small step toward a very exciting direction. So I'll start with some open questions that I think are interesting. So the first one is the question of generalization, in the sense that whether this technique that I described can be extended to related problems such as postgraph or Bondo adjustment. And the second, or perhaps more general question is, for these type of applications in estimation, when or for what kind of, in what circumstances does looking at the graph provide enough information? And the flip of this question is, what do we lose by only looking at the graphs? So these are some interesting questions that I think would be valuable to answer. And with that, I will stop here and I'll be happy to take any questions. Thank you.
Thank you very much, Yulun. It was a great talk. Maybe I can start with questions and then we go to the audience. So I think you mentioned that the first approximation, so approximating Riemannian Hessian with Laplacian with the Kronecker product, you mentioned that that's actually a Gauss-Newton, like Riemannian Gauss-Newton in disguise. Like that wasn't obvious to me. Like, can you provide some intuition? And my second question is, you have two approximations. Which one of them hurts the convergence more? The epsilon one or the delta one? Thank you.
I see. Yeah, thanks. Both are good questions. So to answer the first one, let me try to find one of my backup slides where I have the exact derivation, but I won't go into the detail of like how like each step is derived. But the main way that we can show that this is a Gauss-Newton method in disguise is by looking at each term, each squared measurement residual term. And this slide shows the derivation for the case of chordal distance, but I believe that a similar kind of argument could be made also for the geodesic distance. But the key step in kind of deriving this is by kind of utilizing the property of the Frobenius norm, and then by kind of replacing the rotation variable using the local perturbation. And once we have these local perturbation, we'll replace this exponential mapping with their first order approximation, and then dropping all of the terms that have second order or higher order dependence on this VI or VJ. At the end of the day, you can show that for each edge, there is actually a corresponding kind of a quadratic term that depends on VJ and VI. And once you know this, you can sum over all of the edges. That gives you the Laplacian. So this is kind of a quick derivation for the Gauss-Newton part. For the question about the impact between the two approximation, this is also a good question. I don't know that if I can provide a very exact answer, but one thing I've noticed in the experiment is that the first approximation, which is going from the Hessian to the Laplacian, it depends on the noise level a lot. So, which means that, you know, for problems with very large noise, or maybe for problems where you have some outlier edges, that tends to basically make the Hessian, make the Laplacian-based approximation worse. Yeah.
I see. Yeah. So that's also that can be explained by the connection between that and Gauss-Newton, right? So your residuals are large. Thank you very much. Any questions from the audience? I think we have 2 questions potentially. David?
Hey, Yulun, thanks for the very beautiful talk. This is great stuff. I actually had another question pertaining to the Hessian to Laplacian approximation that you started with. The plot that you showed, that seems like a remarkably sharp approximation, actually. So I'm curious, is that does the result that you've that one, does the result that you have derived hold at the minimizer, or is that actually a global approximation bound over like the entire product rotation manifold?
Right. Okay. So let me clarify the second point first. So the theorem here is showing like in an informal form, but actually this inequality will hold around in a neighborhood around the global minimizer under the assumption that all of the measurement residuals are bounded. And to answer the first part of your question, this kind of is also expected in the sense that here I'm computing the value of delta at the minimizer. And as the noise level converges to 0, the minimizer corresponds to the ground truth rotations. And it can actually be shown that in the case of ground truth, using the ground truth, so evaluating the Hessian at the ground truth rotation without any noise, in that case, the Riemannian Hessian is exactly given by the Laplacian. And that could also be explained from the Gauss-Newton perspective, because the Gauss-Newton perspective also tells us that in general, when the measurement residual are 0, then the Gauss-Newton Hessian approximation is actually exact, right? Yeah.
Awesome. Okay, yeah, that's really cool stuff. Thanks.
Thanks.
Yeah, thanks.
We have another question.
Thank you for the great talk. As you mentioned, actually the entire analysis is based on the delta is small enough, and in reality, delta might not be actually small enough. So, do you have any kind of like some sort of like a remedy to address for the case where your delta might be actually not small enough? And the second question is, you have compared the kind of like previous approaches where you also had estimation theory-based approach, and your approach is optimization-based approach. But in fact, in estimation, you also consider the kind of like probabilistic maybe characteristics of the measurement noise, but it's also, to me, optimization-based method. So what is the exact difference between the estimation theory-based method and the optimization-based method? And if you have any comparison between these two methods, it'll be very, very nice to hear. Thanks.
Okay, thanks. So let me try to answer the first one, which is about the assumption on the noise level. So here, I think by noise level, there could be 2 types of noise. The first one are noise that looks like Gaussian. So these are noise level that is kind of, for example, visualized on this graph here, where, you know, although we are keep increasing the level of noise, it's still 0 mean. It's just that, you know, it's a larger variance. And the result that I'm showing on this slide kind of shows that for that type of noise, this Laplacian actually is a very good approximation empirically. But I agree that kind of in terms of theoretical analysis, the current analysis or the assumption on having small measurement residual could be conservative. And then at the same time, there could be another type of noise, which is outliers, right? So those are also very prevalent in, especially in real world multi-agent settings. So those are kind of harder to deal with because they violate the Gaussian assumption that we typically assume for these type of noise models. But it turns out that we can still kind of handle outlier measurements using some robust optimization framework, such as iterative reweighted least squares or graduated non-convexity. And so I haven't described this in this talk, but in the paper, we also evaluate using this proposed solver inside those robust optimization framework and show that they are also useful for kind of working even in the presence of outlier measurements. So that's my answer to the first question. For the second question, I think that is more general. So yeah, so basically these optimization formulation, which also includes this talk, usually they can be derived from a probabilistic estimation setting. For example, maximum likelihood estimation. But in the end, they only provide a point estimate in the sense that we only recover the maximum likelihood estimate, which is like a single configuration of all of the rotations. So it'll be interesting or valuable to also, for example, have an estimate of the covariance and things like that. And those are, I would say, kind of start to be more relevant or more related to the estimation theoretic point of view. So I'm not sure if that fully addressed your question.
Okay, excellent. I think we might have time for one more quick question if anyone else has one. Going once, going twice. All right, well, in that case, let's thank our speaker again.
Thank you.